let's begin by um, going over what we were doing last time. So last time uh, we started to take a look at the one-dimensional version of the boundary value problem that we were solving. So we said that we are in this chapter we are going to concentrate only on this one-dimensional problem, and we are going to try to figure out ways of trying to solve this problem in an integral sense. So even though we know that this one-dimensional problem can be solved exactly by using direct integration or some other methods for differential equations, but even then we are going to try to solve it in a different way that will help us understand how two dimensions and three-dimensional finite elements work. So we said that this is the strong form of the equations. So whenever we write down the differential equation or the governing differential equation, this is called the strong form along with its boundary conditions. And the way we are going to try to solve this in an integral sense is by using what is called the method of weighted residuals. So whenever, now this is a standard step in all finite element formulations. So the first step you do is take your governing differential equation, multiply it with a virtual displacement function. And if you set this, uh, if you integrate this over the domain and set this equal to 0, then we can make the statement that if if this functional is 0 for all u bar, then we can say that the integrand here is 0 for all points in the domain. And we were discussing a little bit about this, I think, last time with Prashant. So I'm not sure if you guys took a look at the uh, the derivation or the proof of the fundamental theorem of calculus. So I think this is a very important point. So let me actually uh, present it to you in a little bit of a different way. Let's uh, think of it as a little game. So, so let's say you guys are here, I'm here, and let's pretend that somebody else is here. Uh, they have gotten a new calculator, and they are going to play a guessing game with us. So they have a number in their hand, and we are supposed to guess what number that is. Okay? So, but the rule of the game is this. Um, So the rule of the game is that, let's say they have this number r, and the way we are supposed to find out what the number is we are going to give them some another number u bar, just a real number, and they are going to multiply those two together and tell us what the result is. And using this information, we have to guess what that number r is. So let's make any guesses. If we guess 1, uh, the result turns out to be 0. So if u bar is 1, 1 multiplied with r is 0. If u bar is 2, 2 multiplied with r, they tell us is 0. Um, pi, pi multiplied with r, that is 0. 1 upon square root 3, as long as you are guessing real numbers, they keep on telling us that you multiply anything with r, uh, you're getting 0. So now, by now, we have a pretty good idea that r might actually be 0. So the way that we try to prove that r is actually 0 is that we're going to say to them, okay, you have this number r with you. Don't tell us what that r is. Take that r, multiply it with itself, and tell us what the result is. Okay? So what we are asking them to do is take r, multiply it with itself, and they still tell us that the result is 0. So now, to ourselves, we can be convinced that if r square is also 0, then the only possibility is that r itself is 0. Okay, so this is the proof uh, on which the theorem, the fundamental theorem of calculus of variation hinges. So if you extend the same analogy, now instead of this r being a real number and u bar being another real number, if we say that now R is some function, we don't know what that function is, but we are going to keep on multiplying it with whatever functions we choose. So if we choose any function, we can choose one function like this, one function like this. The last time we were taking a look at what possible choices of these functions are. So we could choose any function and we give it to them and they multiply those two together and tell us the answer. So if we say that in this particular case, now again don't tell us what R you have, but if we choose ux is equal to Rx, then they tell us that integral of Rx squared dx from, let's say, 0 to L, that is also equal to 0. If this is true, then the only possibility is that R is equal to 0. And this is an integral way of satisfying our governing differential equation. So now what we are saying is that if R, let's call R as the residual, sigma prime divergence of sigma plus b as a function of x. We are not saying that this is equal to 0. We are defining R. So if we define the residual in this way, and now if we say that for all u bar, if our g times sigma and u bar is equal to 0, then we can be sure that sigma of x plus b is equal to 0. So does that sound familiar? I'm not sure if I've answered your question or if you had some other. Okay. So, all right. So let's go back to this. And the reason I went over this is because this is the basis of all that finite elements that we are going to be studying. This theorem of calculus of variations is very important to us. So we said that, okay, now that if we choose all u bar, then this is going to be satisfied. And we added a couple extra boundary terms. So these boundary terms are nothing but the Cauchy relationship in one dimension. So stress times the normal vector. The normal vector in one dimension is either +1 or -1. So you add those two boundary terms to your functional, and now if you say that for all u bar this must be equal to 0, then we know that in addition to the governing differential equation, the boundary conditions will also be satisfied. And the reason that these u bar functions have to be square integrable is because we are using the theorem of calculus of variations. So we need to be able to take the square of a function and integrate it. So last time I also told you about what other types of functions we could choose for this u bar. So the minimum possible thing is that the function itself has to be square integrable. But we also saw last time that if you take this method of weighted residuals, if you start with this function, we can prove that this is actually equivalent to the principle of virtual work. So we said that we'll take this, we will do integration by parts. So the first step was take your governing differential equation, multiply it with a u bar. The second step is integration by parts. And once you do your integration by parts, you get this term from the first term, and you get a boundary term which actually cancels off with one of the boundary terms we had earlier. And since this boundary term is actually naturally generated from your virtual work, from this functional g, it is called a natural boundary condition. And I also told you that essential boundary conditions are not included in the method of weighted residuals. So essential boundary conditions will be taken care of when we later approximate our solution. So if you do this, you can express the functional that you get in the terms of virtual work. That the first term is the internal virtual work, The second term is the external virtual work, which means that if G has to be 0, then internal virtual work has to be equal to the external virtual work. And I hope that anybody who has taken structural analysis before remembers this relationship. Um, so we also said that U bar has to be 0, so to get rid of the traction unknown at x is equal to 0, we can assume that U bar at 0 should be 0. And then we said that we are now going to introduce the material properties. Up until now, we did not even say that the kinematics has to be linear, small deformation, large deformation, whatever. As long as div s plus b is 0, we can all that principle of virtual work holds. Now we are going to assume a certain type of a material, which is a linear material with small strain. And if we do that, we can write the same virtual work functional in a little bit different way. So now you can see that it is a function of U bar and U. So U bar is the virtual displacement, U is the real displacement, okay? And if we can again show that this functional is 0 for all U bar, if this functional is 0, then the internal virtual work is equal to the external virtual work, which means that our governing differential equation div s plus b is satisfied everywhere, okay? So this is the weak form of the problem statement, what I just said, and I also pointed out that strong form and weak form are exactly equal. We have not made any approximations yet, okay? And there were a couple of other alternative notations. So this is about where we were last time, and we said that now that we want to solve the weak form, this weak form itself is still an infinite dimensional problem. So we have just transformed one infinite dimensional problem to another infinite dimensional problem. And to be able to solve this in an approximate manner, what we will do is we will assume that the solution U can be approximated as a linear combination of some functions. You choose any function you want. We will express our unknown variable, unknown displacement U as a linear combination of all those functions. So here is this approximation. We are saying that we will approximate the real displacement with something called a discrete displacement. This is a discrete displacement where this is being denoted with a superscript h. And you will see later on in finite elements, whenever we make a discretization, we will express quantities with a superscript h. Okay? This is the same notation that the Hughes book also uses. So we are saying that this approximation is going to be a linear combination of all these functions, and we will add one extra function that will take care of our boundary condition at the left end. So some of the choices, you can express this, this summation as a matrix, as a row vector. These are all scalars that you don't know yet. We will be solving for these scalars, multiplied with a vector of functions. So a vector of functions, this is a row vector multiplied with a column vector, you will get the exact same thing that you have here. And yeah, question? So discretization, what I'm saying is I had an infinite dimensional problem first, that I need to find U at each and every location of X along the bar. But now I'm saying that my solution, I'm going to assume that it is a sum of a linear combination of some functions. So in a way, I have discretized it. Although truly speaking, a discretization would be dividing the interval into some parts. So that is it's better to say that discretizing is dividing the interval into different parts. But this is also a type of discretization. So if I express my unknowns in terms of known functions, I have reduced my infinite dimensional problem to a finite dimensional problem. Here I have n unknowns, which are all scalars. So my the number of unknowns that I'm trying to solve for are finite, n. Okay. And here is the condition that how we will satisfy boundary conditions. So we will pick a function h0 right here. You can pick any function. As long as it satisfies the essential boundary condition is at 0, it is good. So we could also take there are some examples of what types of basis functions you could choose. Now let me introduce this term also. These are called, all these functions h, they are called either basis functions or shape functions. So you could choose any type of basis function, shape function you want, as long as it is smooth enough, meaning that it is at least square integrable, or now in this case it has its first derivatives have to be square integrable, and it has to be complete. And what we said about completeness was that if you choose enough number of those functions, then your solution will become more and more accurate. Okay, so we also talked about how to approximate u bar now. So we said that Galerkin came up with this expression. We will approximate the u bar also in the exact same way. That now in this case, this is the linear combination of all those shape functions, all those basis functions, but we are not adding any h0, because u bar, the virtual displacement, does not need to satisfy the essential boundary condition. It needs to satisfy the homogeneous essential boundary condition. Homogeneous essential boundary condition is nothing but this one. We will choose u bar in such a way so that u bar at 0 is actually 0, and we did that to get rid of this unknown. That's why we choose u bar to satisfy the homogeneous essential boundary condition. So there is no h0 here. And again, this is a row vector multiplied by a column vector. These are all scalars. These are also unknown, but we are actually not going to be solving for them. We will take them out common, and we'll say that you choose any value of a bar, my functional g should be 0. So that allows us to solve that function for all values of these scalars a bar. And now all that you have to do is to actually plug this back into your VirtualWork functional. And last time I made an error here. So can anybody point to the error here? This is the Galerkin form, G and W. So all I'm doing is I'm plugging my assumption that U is an approximation. All that I'm doing is I'm plugging that in here. This is my W. So in here you see this is U bar prime, which is the first derivative of the VirtualWork functional, virtual displacement. This is also U prime, which is the derivative of the real displacement. So G is defined in this way. If I want to substitute my approximation for U bar, I also need to take the derivatives there. Okay, so this should be prime, and this should be prime, this should be prime, and this should be prime. So what that means is we have to take the derivative of this term, the derivative of this term, derivative of this term, and all that. All the rest of them you do not have to take the derivative, because we integrated by parts only the first term. Is that clear? Yeah. So make that change in your notes. And now we need to point out that strong form was equivalent to the weak form, but now that we have made the Galerkin approximation, this is an approximate form. Okay. And maybe I can also point out a little bit of a relationship from the very first lecture. We were saying that all these levels of models we have this real life, and we take this building in real life, we approximate it with some mathematical model. So our mathematical model is div s plus b. We are saying that equilibrium must be satisfied. We have all those kinematic equations. Now we have made the discretized approximation. So now we are at this level. So we have discretized our equation, governing differential equation. And then finally, we'll implement it in the computer and see what we get. Um, so this is the second level of approximation, if you want to think of it that way. So Galerki form is the approximation of this. Now you go back in and you try to collect terms or rearrange these terms in a little bit different way. So what we'll do is we'll take this A bar transpose. This is nothing but this term right here. So we'll take this term and we can see that A bar is all constant scalars. It can be taken out of the integral. So what we'll have again inside is this. So these are derivatives that were missing again from the last time's handout. So this first term can be expressed as, you can take out A bar common on the left and you can take A common on the right, and what you are left in the middle is a matrix. And the reason it is a matrix is because this derivative of H, it is this vertical vector right here. If you take the derivative of each function here and you express that as a column vector, that's that H prime vector. Similarly, H prime transpose vector, that would be the derivative of all these functions and then transpose it to make it a row vector. So what we are doing is, this is the column vector, this is the row vector. So column vector multiplied by a row vector, that will give you a matrix. And that's why we have this K, that's called the stiffness matrix. And similarly, you can collect the right-hand side of those terms. Again, take out A bar common from the integral. And if you collect all those terms, you can express them as A bar transpose multiplied with F. Okay? And now you can express your G function in this way. So this is A bar transpose. This is a row vector. Here is a matrix multiplied with a vector. So this K multiplied with this A. Matrix multiplied with a column vector, you'll get another column vector minus F, right? So this is, you can make sure that this equation is 0 for any value of A bar now. Okay, so going back to our game that we were playing, you pick any A bar you want. As long as I can solve this equation, to find A, then any A bar I give, the result of this virtual work functional will be 0. Okay, so this is a standard way of formulating any finite element problem. So all this involved was, expressing our equation in a integral way, and then plugging in an approximate solution. So once you do that, you can make sure that you choose any set of values for A bar. This equation is 0, and therefore your equilibrium equation is satisfied in an approximate way. Okay. Are there any questions on any of the steps that we've done here? This is extremely important that you understand each and every step of this procedure, because these are the types of things that I'll ask you to code, solve on the homework problems, maybe on the exams. So you have to understand each of these steps clearly. So let me recount all those steps, and now this is, we don't have a handout for today, so most likely from now on we'll go much slower. The earlier part was all a mechanics review, so I gave you extra handouts. So keep taking notes along with me from now on. So all right, so the steps for the method of weighted residuals. The first step we said was take the governing differential equation, multiply with some virtual displacement function ux, and integrate it over the domain. Okay, and that step is right here in the first the first line. We took the governing differential equation, multiplied with u bar, added some boundary terms, and we came up with, sorry, where is that? Yeah. So what we get is the the statement of the method of weighted residuals. So this is the first step. The second step that we did was integrate our functional g, and this will actually give us g of, let's say, sigma and u bar. So integrate the first term in our functional by parts to balance the derivatives. So what I mean by balance the derivatives is that if you go back and take a look at this chart, here the derivatives on u bar and u, they are balanced, meaning they both have been taken, we are taking the first derivative of both of them. Earlier what we were doing was u bar multiplied with sigma, and sigma is proportional to, or sigma prime, u bar multiplied with sigma prime. So that was the second derivative of u. So what we've done here is, after we integrate by parts, we have balanced the derivatives. So, and the reason we try to balance the derivatives is because ultimately we need to choose all these types of functions. And where are my spaces that I was talking about? Yeah, here. Now you can see that once you've balanced your derivatives, both those functions have to belong to this space. U bar, which is the virtual displacement, and u, the real displacement. Both of those functions have to belong to this H1 space, meaning if you take the derivative of u bar and the virtual and the real displacement, both of those derivatives have to be square integrable. And there is a relationship between these spaces also, so maybe you can take a note of that also. So if you go from H0, which is the square integrable functions, to C0, then you have restricted your space a little bit. The C0 functions are continuous functions. Okay, every continuous function has to be square integrable, but every square integrable function need not be continuous. So the second restriction is this way. If you further restrict your space to H1, then you have ruled out some continuous functions. So what this means is that there are functions which have first derivative which is square integrable, but they are not continuous. So if we move this way, we have further restricted our space. If we go this way, then it is a further restriction. Now we are saying that not only do all those functions have to have the derivative that is square integrable, but the derivative also needs to be continuous. Okay, so C1 functions are normally encountered in beam problems. So this is the sort of relationship that holds as we keep on following the arrows, going from here to here. We've restricted the class of functions that we can choose. Then here, here, and so on. You keep on restricting your classes of functions that you can choose. Okay. All right. So going back to the steps that we were doing, we have integrated by parts to balance the derivatives. And now that the derivatives are balanced, we can choose the most general class of functions, right? So if both of them are H1, then we can stick with this class of functions. Earlier we had u bar, which had to be square integrable, and u, which had to be at least twice differentiable, C2. So our class of functions was very restricted. But now that we have done our integration by parts, we can choose some more functions in our space. Okay. And finally, the third step was approximation. Once you approximate your real and virtual displacements as a linear combination of some functions, then you can plug that back into the G function and calculate your stiffness matrix, your load vector, and you can solve the problem as finally you have the solution U, or A in this case. A is the vector of unknowns, which will be equal to K inverse times F. So approximation was that U bar as a function of X and U as a function of X can be approximated as a sum I is equal to 1 to N of sum AI times HI X. And you can interpret those two approximations are a little bit different because of the H0, but this is essentially the approximation that we've made. And finally, when we calculate, when we plug in this approximation, what we got was that K A is equal to F. So if you solve this equation, you will get all these unknowns A. And now that you have all these unknown scalars A, you can go back and plug that back into your approximation, and you will have the solution. Okay. So let's take an example of this. Does this problem look familiar to you? We were talking about this problem in maybe the second or the third lecture. That this is a bar that is hanging from the ceiling. There is a body force, its own self-weight, and we are applying some end traction to it. The bar's length is L, and we are trying to solve for the displacement at every point X along the bar. Okay. And if you go back and take a look at the last slide from chapter 1, this was the problem that we had already solved. This is the same bar, same types of self-weight loading, let's say 10, and we solved this by using a direct integration. And in your homework too, you have the problem 3, which is also solving it in a little bit more approximate manner. So if you solve this, we already know that the exact solution should look like this. Okay. So now we're going to use our method, the method of weighted residuals, and try to compare the solution that we get from that method with this exact solution. So does anybody remember what this process is called? We have the exact solution, and we have an approximate solution. We want to make sure that the approximate solution meets. Is that verification or validation? So it's a verification, right? Because we have the exact solution, we want to verify that our approximate solution is the same, or approaches to that in some limit. The validation part was at the first step. You have some real life material, real life structure. You come up with a mathematical model that is div s plus b. So you have to conduct experiments to validate that. So what we are going to do now is just verification. All right, so this is the problem that we are trying to solve. And now the first step, what are we going to do? We're going to take our differential equation and we're going to write it as G U U bar, which is defined as integral 0 to L U bar times the differential equation, which is this. This is nothing but div s plus b multiplied with U bar, and there's a negative sign here, minus U bar at L and traction at L. We are going to again neglect the traction at 0 because we are going to choose U bar at 0 to be equal to 0 again. So once this is the first step that we just talked about. Now we do our integration by parts, and what we end up with, if you remember, is 0 to L U bar prime that is the first derivative of u bar times this term, the stress. This is the internal virtual work minus integral 0 to L of u bar times b dx, and let me lump these two terms together, so I'll have plus u bar at L TL. This is the external virtual work. So this was the second step, integration by parts, that we just talked about. Okay. Now we are going to introduce our approximation. So we're going to say that ux is equal to, or a discrete version ux. It is approximated by the discrete version ux, and the discrete version is equal to the sum of linear combination of some functions. So let's choose these functions to be polynomials. Okay, so we're going to say that I is equal to 1 to n a I h I x, and I'm going to choose my hi functions like this. So h1 is x divided by L, h2 is x divided by L square, h3 is x divided by L cube, and so on. And if you plot these functions, what they will look like is 0 to L, and this is 1. So the first function is x over L. So that is a straight line going from here to here. The second function is x over L squared, which looks somewhat like this. The third function is x over L cube, x over L4, 5, 6, 7, whatever. And slowly you can see that the basis that we have chosen in this case is, the basis functions that we have chosen in this case are not that good, because we are choosing polynomials of higher and higher order, but they start to look like each other. So when we try to approximate our solution, we might not get better and better results as we keep on increasing the order. But anyway, let's take a look at what happens if we choose these functions and plug them into our equation. So we have chosen this approximation, and the fourth step was to actually solve it. But before we can solve it, we need to form our matrices. So if you plug this into this weak form that we have here, what you will get is that G of A vector and A bar vector has to be equal to A bar transpose times this equation, right? So here this A bar transpose is nothing but A1, A2, all the way. A is the unknown vector that we are going to be solving for. This is without, this is the real displacement. And we will decide on the value of n later on after we form all these matrices. So the matrix K, if you take a look at the last step from last time, this is the K matrix. This K matrix is integral 0 to L C and the derivatives of the shape functions, the derivative of the h functions that we have taken. So what do we get if we do that? K is integral of 0 to L C and the first derivative of these functions. So what is the first derivative of this function? What is the derivative of h1 with respect to x? 1 over L. The derivative of the second function, 2 x over L square. Similarly, 3x square over L cube, and so on. And the general formula would be, at n, it would be equal to n times x to the power n minus 1 over L to the power n. So this is our H prime vector. And now we are going to have the same vector but in a transpose way. So we have this 2x over L square and so on all the way up to n times x n minus 1 over L to the power n. So this is the last term in our approximation. And if you can see that this term in the curly brackets, this is a column vector multiplied with a row vector. This will give us a matrix. Okay, and each term of that matrix has to be integrated from 0 to L. So if you try to calculate, let's say, the I comma j term in this matrix, so let's call that term Kij. That would be equal to C integral 0 to L. Now the ith term in the column vector is going to be I times x to the power I minus 1 over L to the power I. And the jth term in the row vector is going to be j times x to the power j minus 1 over L to the power j. Okay, does that make sense? And then if you take the integral of this, what do we get? You can multiply the powers of x together, so you would get x to the power I plus j minus 2, right? X, and if you integrate that, what you would get is I multiplied with j over L to the power I plus j. That's all I've done is taken out the constants. And now I'll integrate the x term. So this will be I plus j minus 1 over I plus j minus 1. And I need to take the limits of this term from 0 to L. Does that sound correct? Okay. And if we calculate this term, after we take the limits, we can see that what we'll end up with is the numerator will have I multiplied with j over L, because L from the numerator will cancel off, and I plus j minus 1. This is what we will have after you take the integral of all those terms. Okay? And if you start to write out the what the matrix looks like, we get something like this. We can pull out L common and now start plugging in the values. The first row and the first column, I is equal to 1, j is equal to 1. If you plug in I1 and j1, what you get is 1. The second entry here would be I is equal to 2, j is equal to 1, and if you plug that in, again you get 1. And I'll restrict this matrix to a 4 cross 4. Similarly, if you plug in 3, the 3 comma 1 vector, that would be 3 multiplied with 1, that is 3 in the numerator. Denominator, we have 3 plus 1 minus 1. Again, 3 divided by 3, so that's 1. Similarly, we'll have 4 divided by 4, 1. And if you take a look at this matrix, it doesn't matter if I change the order of I and j. It is symmetric in I and j. So I can simply write down this matrix as a symmetric matrix. Now the 2 cross 2 entry, that would be 2 multiplied by 2, 4, divided by 2 plus 2, 4, minus 1, that's 4 divided by 3. Okay. The next term would be 6 divided by 4, 8 divided by 5. And since it's symmetric, I know that this is 6 divided by 4. This should be 9 divided by 5. And 12 divided by 6. And this is symmetric, so this is 8 divided by 5, 12 divided by 6, and what's the last term? 4 cross 4, that would be 16. 16 divided by 7, right? So all that we've done here is that we have taken a matrix. This is a we are just going to consider up to 4 terms. We might consider just 1 term, 2 term, 3 term, but we are going to consider all the way up to 4 terms. So finally, we have still 5 minutes, so hopefully that's enough time. We can also express our f vector as 0 to L. So our f vector is going to be all this. Approximation that you have to enter will be right here. So this approximation can be entered as the h vector times the body force, and plus the h vector evaluated at L times the end fraction at L. So if we write it out as a matrix form, what we are doing is integral 0 to L, all these shape functions, x over L square, x over L to the power n, multiplied with one scalar b. B is nothing but the density times gravity. And we have to take that integral from 0 to L. And finally, we have this. So what would this vector be? H evaluated at L. If I plug in the value of x is equal to L, all these terms go to 1, right? So we'll have 1, 1, 1, all the way down to 1. And we have what is remaining is this TL, that is the end traction. And end traction in this case, we chose it to be equal to, I think this is supposed to be 10. So let's keep it at 10. The body force, we said, sorry, I didn't mention all this. Density is 1. We're going to assume that G is 10. The value of C we are going to assume at 1. And we are going to say that the displacement here is fixed. So U0 is 0. And finally, the traction at L is equal to 10. And we are trying to solve this problem. So if we do that, what we get for F is something like this. So the first term is, after you do the integration and all that, I'm just going to write out the final answer. I want to show you how it looks like. So 100 divided by 3. It's just easy to integrate this first term and add this term TL, which is equal to 10. And so on all the way up to 100 over n plus 1 plus 10. So this is our force vector, and this is, we finally have our force vector, and we have our stiffness matrix, K. Now all we have to do is to solve for our unknown variables. So this is the fourth step of our solution. A is nothing but K inverse times F. And if we calculate A in this manner, we know that our virtual work functional will be satisfied for any value of A bar. Okay. So let's take a look at what this solution looks like. So I've already coded up what this looks like. So this is a small Matlab program that I just wrote. This is your x values starting from 0 all the way to 10. And this is the exact solution that we calculated from the very first chapter for that problem. Okay. So if I plot these, if I plot this exact solution, what it looks like is this. And by the way, those of you who are new to Matlab, this is a way that you can use the debugger to see your output one line at a time. That will be very helpful for you in catching errors. Okay. So if you run your code one line at a time, and now I'm going to plot. So this is the exact solution what it looks like. From 0 to 10, under self-weight and applied traction, the displacement looks like this. Okay, so finally, this is the K matrix that we just found out. I've created the K matrix. This is the F vector that we just found out. And now I'm going to start to take, trying to start to solve our problem. So if I consider only one term, just a linear approximation, okay? That is the solution if I take only the first term of K 1, 1 and invert it. And if I do that, what I get is this. So this is the, clearly it's a linear approximation to the exact solution, okay? Now let's consider two terms. So I'm going to take the first 2 cross 2 of my stiffness matrix. If I do that and plot the solution, it is extremely close to the exact solution. And you can zoom in and you can actually take a look that this green curve was the two-term solution, which is a quadratic solution. The black was the exact. And another point to note here is that this approximate solution actually matches the exact solution on the dot, at least in one dimensions, where at the regular intervals that we chose to approximate fit. And finally, now if you increase the order to 3, so 3 does not make a difference. The same curve that you have here, it just overwrites it with 3 terms. And similarly, the 4 terms, it does not help either because you've already reached the best possible approximation. All right, so let's stop here and we'll meet on Friday.